So we'll be looking at the JEE Test 4 solutions for electrostatic potential and capacitance questions. Few questions are of a very general variety, whereas few others are unique. So let's start with them. The first question, a system of three charges. This has been asked in one of our previous tests, I presume, how to go about it. We first write an expression. There's a shortcut also, which shall be revealed later. The potential energy expression is, I will make as many pairs as possible. How many pairs can I make? I can make one pair, two pair, and three pairs of charges. So overall potential energy would be K times minus q square by d square, and then the distance between plus q and q, how much would that be? This whole distance is a d, whereas I can say this distance is a d by 2. So between plus q and q, the distance is capital D minus d by 2. So their contribution would be plus k q q by d minus d by 2. We should not have put a square here because it's potential energy, it's a linear term. And then what about minus q and plus q? Uh, for that, I would need a distance between these, right? So how much would that be? Uh, Between plus q and capital Q, it would be d plus d by 2, whereas between minus q and capital Q, it would be d minus d by 2. So I put all these terms on the screen where the distances between each pairs of the charges are written. One between plus q and capital Q, it is a d plus d by 2, whereas between minus q and capital Q, it is d minus d by 2. I will simplify these and then use a condition that d has to be very, very much greater than capital D is greater than small d. That is the one way of arriving at the things. There is a way to eliminate also. Elimination would give us, let us say I put the capital Q itself as 0. Right? I will assume this capital Q is 0. Then the only charge left is plus Q and minus Q. Their potential energy should be minus KQ square by D. Right? But option C says if I put capital Q as 0, I get plus KQ square by D. So I can eliminate only option C with this because rest all others gives minus KQ square by D only if I put capital Q as 0. What is the other way to eliminate? Well, you can say this. The What are the possible interactions between the various charges over here? Possible interactions as in one will be attractive, other will be repulsive, so on. You see that plus q and capital Q always repel, whereas this minus q and plus q and minus q and capital Q always attract. So overall, this system is an attractive system where, because it comprises of more pairs which are attractive in nature than repulsive. So its potential energy for any attractive system should be in a negative sign. So I would rather favor this minus and the minus A or D since it has overall a negative sign. But I can't eliminate further than that because even in option 8, it's QQD by 2D square. Here is QQD by D square, just a numerical coefficient difference. For that, I have to do the conventional way, the shown above. Make as many pairs of charges and then designate the distances, make mathematical manipulations, and where you'll use the fact that capital D is greater than small d. So this is for question number 1. Question number 2. For question number 2, there is a direct formula. Whenever such capacitors are given, I have elucidated that in the other video too. There are two possibilities. I connect plus to minus, or I connect to plus to plus. Right? So in these two cases, I will first find a common potential. Common potential for this case is C1V1 minus C2V2 by C1 plus C2. All right. So here, let's straight away take the product. C1 is C, V1 is V, C2 is 2C, V2 is 2V. Let us take their product. C1 V1 minus C2 V2 by C1 plus C2 because they are connected positive to negative. So C into V is CV. 2C into 2V, right, is minus 2CV. So overall, what I get is minus 2CV by, sum of them, 3C, 2C plus C, 3C. So I get over minus 2 by 3. But I won't give a much damn to this negative sign because I know potential's magnitude is important than its sign. So the common potential of the two capacitors is 2V by 3. So I know that potential across this is 2V by 3. This is also 2V by 3. Capacitance of this is C. Of this is also, this is 2C. Then how will I calculate the final energy of the configuration? Well, final energy is half CV square for this capacitor plus half CV square for this capacitor. The C values are different, but V value is the same. This is how much the formula will save the trouble. This happens due to the rearrangement of the charges. Both the capacitors will be in parallel connection and potential across them will be the same. Okay, so that is um, question number 2. Had they interchanged it, there's an interesting thing here. Had they charged C at 2V and 2C at V, had they just interchanged these values, then see that their CV product becomes the same, 2CV, 2CV. Then this formula will give you zero voltage. That means the charges have nullified each other and the final energy would be zero because common potential would turn out to be zero in that case. Interesting. So the order really matters. So we find a common potential, then use sigma of half CV square, summation of all half CV square. The third question. The third question, there is an interesting way to look at it. First, I will do a general result, which we will use perhaps in all our future discussions. Let there be two plates. At I give Q1 charge to the first plate, Q2 charge to the second plate. Both are conducting plates, so charge would spread on both the surfaces. The first surface, second surface, the third surface, and the fourth surface. Whatever charge I give to the conductor the charge spread. The charge spreads itself to both surfaces of the conductors. So, how to find the charge distribution in this case? How much of Q1 charge is there here? How much of Q2 charge is there, etc. I will tell you a very famous result. The result is this. If I give, you know, uh, Q1 and Q2, this is valid only if I have two conductors, okay? Q1 and Q2, the facing faces, as I call it, these two faces will have equal and opposite charge. What would be that charge? Q1 minus Q2 by 2, and this one shall be Q1 minus Q2 by 2 ka negative, right? This phase will have Q1 minus Q2 by 2, that phase will have Q1 minus Q2 by 2 ka negative. What will happen to this phase? It will have Q1 plus Q2 by 2, right? Because when you sum them, you shall get Q1. And when you sum it over here, it shall be Q1 minus Q2 by 2 ka opposite. Okay, so the facing faces will have equal and opposite charges, Q1 minus Q2 by 2 and minus Q1 minus Q2 by 2, whereas the opposite faces, one which are not facing each other, will have Q1 plus Q2 by 2 and minus of Q1 minus Q2 by 2. For a system of n plates, here there are only two plates. What if they give you three plates? Then how to find the charge distribution then? Here is where a general result would be useful. Whatever might be the case, the facing, you know, faces, as I call it, the how many pairs of faces are facing each other? This one and this one. Whatever faces of the surface are facing each other, there they will always be equal and opposite charges. Suppose I gave Q1 charge to this plate, then this face will have, let's say, Q. This plate definitely should have minus Q. Okay, then what about if I gave Q2 charge to this plate? See, total charge should always be Q2. Whatever charge I give to this, the sum should be always Q2. So here it would be Q2 plus Q. right? So, and this phase shall be minus of Q2 plus Q. Reason is the facing phases should always have equal and opposite charges. And we will illustrate at the end of the video as to how to go with this. But let's focus on the problem in hand first. So, given any two, just two sheets, the charge on one of the face shall be Q1 minus Q2 by 2. Charge on the other would be exactly the negative of it. So if I apply that 2 and 4, okay, I get these charges to be, let us say, plus 1 microcoulomb and minus 1 microcoulomb if I substitute. Remember, for capacitors, we had done this in the very beginning. For capacitor plates, we consider only the inner faces. In all our derivation and discussion, we focused only on the inner faces and not on the outer ones. So what is the charge on the capacitor now? I will say charge on the capacitor. Remember, charge on any one plate, inner plate of the capacitor. Charge on a capacitor is 1 mu c, and the capacitance C is also 1. So how will I find the potential, the difference developed? What is the potential difference between these two facing phases? Q equal to CV, right? And that would give you voltage also as 1. So how did I arrive at this? First, I calculated the charges on the inner phases. They should be equal and opposite. For that only, I can apply Q equal to CV. I calculate Q, C is already given, I find out V. That is the approach for 3. Wait till the end of the video where we will discuss the N charges in detail. Now we will move on to question number 4. In question number 4, the total charge stored in the system is 750 microcoulomb. Voltage across C2 is 20 volts. They're asking what is the charge on the capacitor C2. They are given you voltage, they're asking you charge. Let me clear this up before we proceed, right? So note that they haven't given the value of C2 at all, right? They haven't given value of C2. Now, how to break our head to find the value of C2? They haven't given value of C2 at all. They have just given potential between this is 20. Well, if potential across C2 is 20, I can say potential across C3 is also 20. Reason? Because both of them are parallel, right? So if I know voltage across 8 is 20, what shall be the charge? Q equal to CV if I apply for C3. Charge on C3 is 8 into 20, around 160 microcoulomb. Charge on C3 is 160 microcoulomb. But remember, if the total charge is 750 means this has already 750 in it. So this entire system should have 750 on it. There is already 160 on C3. Therefore, the remaining, if I add charge on C2 to C3, I should get 750. Reason, the equivalent of C3 and C2 is in series with C1, and both these capacitors have the same charge. So 750, if it is this, 750 should be the 750 is the charge on C1. Then the total charge on this system, if I reduce it, it should also be 750. So QC2 plus QC3 should be 750. And I know QC3 is 160. Okay. So when I subtract 750 and 160 or 160 from 750, I'll get option B, 590. Okay, 590. From this, I can also calculate the capacitance of C2, Q equal to CV, and so forth. So this is how you can attack this. Charge on C3 plus charge on C2. Charges are different, but the sum total of them should be equal to 750. Okay, that is question number 4. Why? Because the equivalent of C2 and C3 is in series with C1, and we know charge on the capacitors in series are the same. So C1 will have 750, even the equivalent should have 750. Sum of the charges should be 750. We already know 160 is on C3, remaining should be on C2, so it should be fine. That's question number 4. Question number 5. I hope you have read the question. All I will do is I will substitute K as 1. If I put K as 1, then I amn't really changing anything, you see. Initially, the voltage between this and this was same. If I put K equal to 1, if I put in air, nothing is changing. So the voltage, initial voltage will not change if I put K equal to 1 only. Which of the options I will eliminate B because it says it's V throughout. Which between AC and D will give V when I put K equal to 1? And that shall only and only be D. Hence, the new potential difference of the system should give you D. I repeat, how did I arrive at it? Well, I just assumed K equal to 1. If I put K equal to 1 there, I am really changing anything in the system. So the voltages shouldn't change. Therefore, it is D. That is the fifth question. Now, moving forward, we have question number 13. Energy dissipated in the circuit is, right? You see, there is initially this part is dead because switch is active, only this part we should consider. Initial charge given is Q. How do I find the energy dissipated when the switch is put to B? We have a formula for that. Change in energy is always half C1 C2 by C1 plus C2 times V1 minus V2 the whole square, where V1 is the initial potential difference across C1 and V2 is the initial potential difference across C2. In this situation, the C2, the 3C1 doesn't have any battery with it initially. So how will I proceed? C1 is C, V1 is epsilon, and C2 is 3C, V2 is 0. Okay. But in the option, there is no signs of epsilon. Here is where I will convert epsilon in terms of charge stored. Charge stored. How will I do that? We know Q is equal to CV. So Q is equal to C times epsilon. Epsilon is equal to Q by C. So I will put not epsilon, but instead V1 as Q by C, and I'll have my answer. This is the one-shot approach to do any such capacitor flipping questions. This should be helpful even if the capacitor 3C had an initial potential difference. Had this 3C been connected across any battery, then V2 would be non-zero. So this one thing will help in a lot of questions. Now, question number 14. In the given figure, what is the work done by the battery? Work done by the battery is always charge difference. Charge difference is the charge in the final configuration minus charge in initial configuration into potential difference of the battery, which is 4. Where did this come from? This came from potential energy equal to QV. Work that done by battery is always in the form of potential energy. How much did it lose? It pushed Q through V. V is 4 over here. It pushed Q through V. So total energy spent by it is QV. How to find delta Q? Well, initially the switch is open. So the physics says that these 10 and this 10 are in series with each other. How? Because I can imagine the plus plate pulling one electron from here. That electron should go and deposit itself over there. So the charges developed on these two are equal and opposite, so they are in series. If they are in series, what is the charge in the system? 10 and 10 are in series, so equivalent capacitance initially is 5. So initially equivalent capacitance is 5 and the potential difference is 4 volt. How will I find the charge? Initial charge is CV. So initial charge would be around 20 units. What about the final charge? In the final configuration, I close this switch. So what happened is the upper plate of this capacitor is connected to 0. Lower plate is also connected to 0. Effectively, I have not the potential difference between the two plates of this 10 microfarad is zero. The only active, the only active part in this whole circuit after closing the switch, after closing the switch, is just this, right? The charge won't even flow through this because potential difference across this is zero. So the active path is that. What is the capacitance then? 10. What is the voltage then? 4. What is the final charge? Final charge Q final is CV. So it would be 40 units. 40 units. So what is the charge which swept through the battery? Charge which swept through the battery is the difference between the final and the initial charges, which is 20 coulombs or 20 units. So the battery pushed 20 units of charge through 4 volt of potential difference. So the total amount of work numerically turns out to be 80 units. You substitute micro, nano, whatever it is, but that doesn't matter more than the physics. Physics says the work done by a battery is always a charge which flowed through the battery and multiplied by potential difference. Initial charge in the system was 20, final in the system was 40. So additionally, some charge redistribution happened. It has to happen through the battery. So the difference in charges is 20 and 20 into 4 would be 80. So the 14th one goes with the 15th one. In the 15th one, I have potential at n to be 0. I will draw equivalent of all this. It will be handy, right? Uh, so this is C, this is grounded, and this one shall be C, 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 three C's in series. So it will be C by 3. Now this C by 3 and this C are in series with each other. Again, the same physics. The positive plate, imagine pulling out one electron. The same electron should go and sit on this. So the two capacitors are in series. The voltage across C by 3, voltage across C by 3 is main voltage 10 into the other capacitance C by sum of the two capacitances. This is a trick. Main voltage into adjacent capacitance by sum of the capacitances. So this would give around 7.5 volt. So the potential difference across the plates of this capacitor is 7.5. So VA, potential at A, minus, okay. And now you see I need the the potential at n. Well, what is potential at n? That is 0. V0 is equal to 7.5. That is a meaning of potential difference, right? Potential at A minus potential at O should be equal to 7.5. This is anyway given to be 0. Therefore, the potential at A is 7.5 volt. That is answer to the 15th one. Here we exploited a trick which is voltage divider trick in capacitors. Now question number 16. Three capacitors, each of 4 microfarad. Our intuition can help in this. Suppose I have 4 and 4 in parallel, then the overall capacitance would be 8, but given itself is 6, right? So what I do is I will say 4 and 4 are in series and connect a 4 in parallel. So 4 and 4 in series, equivalent of this becomes 2, and 2 is in parallel with 4. The algebraic addition will give you 6. So 2 should be in series and 1 should be in parallel. Then I shall obtain 6 microfarad as the equivalent capacitance. So 16th one goes with D. Now 17th one. In 17th one, I should imagine a battery which is connected across this terminal. Whatever charge comes from the positive terminal, it gets divided into three halves, right? But you see the potential between each of these plates is the same, which is the battery voltage. So each of these capacitors, one in black, one in red, and say one in orange, all these are capacitors in parallel. So how do I find equivalent capacitance? Equivalent capacitance is algebraic addition of the three capacitors. And how do I find individual capacitance? Look at the options. Everywhere there's epsilon naught A by D. So assume epsilon naught equal to A equal to D as 1 unit, right? And then remember the medium between the plates are they would have made it more complicated by putting in dielectrics that they haven't made. It is just air. So uh, it's a plain addition. For C1 it would be epsilon naught, it is a by 3. So uh, 1 by 3, but epsilon naught is anyway 1, and d is, you know, just d. It's just 1 by 3. And for C2, area is again a by 3, but remember the distance is not d, it is 2d. You need to take this total distance, 2d, d plus d, 2d. So epsilon naught a by d, this will be that. And what about this plate? Again 1 by 3, but it will be now 3d. So 3. So 1 by 3 plus 1 by 6 plus 1 by 9. The LCM of all these is around 9. And but, I mean, LCM of all these is 18. The only option in 18s is this. So that might seem the more appropriate one until unless you simplify. So this shall be 6. That shall be 3. This shall be 2. And 11 by 18. Yes, C is the right choice. The LCM of 3, 6, and 9 is 18. The only one option satisfying this is C. This is how quick we can make this job. That is question number 17. Going forward. Question number 21. Question number 21. It is a parallel plate capacitor, and it has air between it. Its capacitance is 9 picofarad, it seems. Now, the separation between its plates is D. One of the dielectrics has dielectric constant and D by 3, while other one has dielectric constant 6 and thickness 2D by 3. What is the capacitance now? Well, this also calls for a special trick. Right? Um, Let me make this one dielectric. Let me make the other dielectric. The distance between the first dielectric has a thickness of D by 3. What should be the second dielectric thickness? It should be D minus D by 3. It should be 2D by 3, of course, right? D by 3 and 2D by 3. They would have made this even more complicated by not giving you 2D by 3. It would have been two dielectrics and air, but no, they have not made that. So this is it. How to find capacitance of this capacitor? Trick is the capacitance in this case is epsilon naught A for sure. What is the distance with that red dielectric? D by 3. I divide this D by 3 with its own dielectric constant. What's the dielectric constant D by 3? It is 3. Plus, what is the dielectric constant of the green one? For green one, dielectric constant is 6 and the thickness is 2D by 3. So this is a new capacitance. Distance thickness of the dielectric by its own dielectric constant. Is there anything else? Nothing. Now you will see that this can be simplified, but it will have epsilon naught A by D. That the answer will be in terms of epsilon naught A by D. They have not given A at all. How to go? We have a rescuer. They have given the original capacitance. The initial capacitance Ci is epsilon naught A by D, and we know the value of this, that is 9 picofarad. So whatever you get here, it will be in terms of epsilon naught A by D with some numbers and coefficients. But all epsilon naught A by D's you can put together and put it as 9 and you get the answer. This is the most time optimal approach for question number 21. Now question number 22. The magnitude of the electric field due to a point charge Q having a charge equal to sum of the charges on 4 mu F and 9 mu F. Hold on. Well, this point charge Q doesn't have anything to do with this circuit. The point charge Q is a different case. It is there in some other place. They are just telling capital Q is a sum of charge on 4 and 9 capacitors. 4 and 9 capacitors. If I find these charges, I would have found Q. After finding Q, what should I do? I should find electric field at a distance of 30 meters from it. In other words, I should use E equal to KQ by R square. R is 30 given, and then find the electric field. So how to find this Q? This Q is nothing but charge on 4, sum of charge on 4 and 9. So somehow if I find 4 and the charges on these two, then I would have found out the Q, then I put E equal to KQ by R square from electric charge and fields, and then arrived at the answer. How would I find charges on 4 and 9? This is what we'll be looking at now in the most, again, time optimal, time economical approach. How to find charge on 4 and 9. Okay, so here it goes. Uh, we know 8 volt is being applied across this terminal. So I can imagine this also having 8 volts, right? Because the potential of this point and this point is the same as this point and this point. So I can imagine this assembly to have 8 volts across it. What is the equivalent capacitance of 3 and 9 in parallel? It is 12. So I will simplify 4, 12, and this is in parallel, or this is connected to a 8-volt battery. That's enough. Now I can find charge on 4 because 4 and 12 are in series. What is 4 and 12 in series? 4 and 12 in series would give you product by sum. 12 into 4 by 12 plus 4. 12 into 4 by 12 plus 4 would give you 48 by 16 or 3. 3 microfarad is the equivalent capacitance and voltage is 8. So Q on 4, Q equal to CV is C3, I mean capacitance C and voltage 8, which is 24 units. So the charge stored in 4 is 24 units. Okay. Now a difficulty. The difficulty is how to find the charge on 9 only, because they have asked 4 and 9. Here is where voltage discussions will come useful. I will just find the voltage across 12 now. What is the voltage across 12? Main voltage across 12 is main voltage 8 into opposite capacitance, which is 4, by sum of the capacitances 4 plus 12, which is 16. Right? So I get voltage across this assembly, this parallel assembly, or this 12 volt, 12 farad is 2 volt. Voltage across 12 is 2 volt. So what would that give me? That would give me voltage across just this assembly, which is 2 volt. If 2 volt is there between these points, even 3 microfarad will have 2 volts and 9 microfarad also will have 2 volts opposite it, against it. So what would be the charge stored in 9? I know potential difference across 9 is now 2 volt and capacitance of 9 is 9 microfarad is 9 microfarad. How would I find the charge? Charge is CV, so it will be totally 80. Q equal to CV. 18. So what is the charge stored in the 9 microfarad one? It would be 18 units. Now what is the sum of the two charges? Sum of the two charges is 24 plus 18. 24 plus 18 is 42. And this 42 is exactly what they need. The capital Q charge is sum of the individual charges, 24 plus 18, which is 42. And hence, right? Hence, the charge stored in the charge stored or the charge which I need now is just this capital Q is sum of charge on 4 plus charge on 9. Charge on 4 I found out is already 24. Charge on 9 is 18. So total it is 42 micro coulombs. Now, how will I find the electric field? E equal to K 9 into 10 power 9, Q 42 into 10 power minus 6 by R squared, which is 900. That would be the answer for 22. It is not a lengthy one. They have made it tricky by making you think that the point charge Q has to do something with the circuit. It has nothing to do with the circuit. Point charge Q is not is somewhere else, but the magnitude of that charge is sum of the two charges on 4 and 9. So this whole thing was just to club electric charge and fields and electric potential capacitance concept. So how to find charge on 4 and 9, you got to know a brief recap. First, I will imagine these 2 points to be connected by simply 8-volt battery. Find its equivalent. If I find the equivalent, then I can easily find the charge on 4. How will I find charge on 9? I will use a voltage divider trick, which we discussed earlier, and then find potential across this combination, which is 2. So even 9 will have 2 volts opposite it, and hence the charge stored will be 9 into 2, 18, 24, 18, 42. Total charge. Okay. We now come to question number 23. In question number 23, standard setup. C1, C2, C3, you take them loops. This is first loop and second loop. I see that voltage between C1, C2 is same and voltage between C2, C3 is same. Therefore, all the three capacitors are in parallel. So equivalent capacitance should be C1 plus C2 plus C3. Done. Now, if I introduce 3 mm thick slab, in order to maintain the same potential difference, the distance between the plates is increased by 2.4 mm. Okay. So, uh, how can I look at this? Voltage still hasn't changed, it seems, even after introducing the uh, uh, the 3 mm thick slab. Um, Now, how to approach this? Well, if the voltage hasn't changed, then nothing really hasn't changed for C equivalent. Remember, C equivalent depends only on C1, C2, C3. We know Q equal to CV, right? And we have maintained constant. And in this setup, it's maintained at a certain potential difference. In this setup, Q is also constant. So if I introduce a dielectric and do anything with it, then individual C has to be the same. So capacitances has to stay the same. Or the equivalent capacitance of C1, C2, C3 after reducing the 3 mm thick slab has to be the same. Now, what is a new capacitance? New capacitance is C equivalent in mu epsilon naught A by what is the thickness in air? Thickness in air is 2.4 mm divided by the dielectric constant of air, which is 1, plus thickness in dielectric is 3 and its dielectric constant is K. This is the new capacitance of C1. C2, it would be the same, epsilon naught A 2.4 plus 3 by K. Okay. And what about C3? C3 also same. It is epsilon naught A by 2.4 plus 3 by K. So this is how we can simplify. Now I can say, and what about C1? Because all these are in terms of epsilon naught A's and C1 isn't. Well, we can do that also. C1 equal to C2 equal to C3. I can say they are epsilon naught A by D. What is the initial distance between the plates? Initial distance between the plates should be 3 mm because once I fit in 3 mm, the definitely capacitance would increase. To retain the same capacitance, I increase the separation distance is increased by 2.4. So initial distance is 2.4 epsilon naught A by initial distance is 3, whatever the thickness of the slab is. So I put these C1 equal to C2 equal to C3 to this, and then the concept that the equivalent capacitance hasn't really changed, and then you can find out the dielectric constant of the slab. A long question, but yeah, the concept is this: capacitance hasn't changed. Now, question number 24. Well, such questions have a template where we call this as group of capacitors. How will I address group of capacitors question? Well, this always goes like this. I will assume there are, m number of plates in series, and then there are n branches of such groups connected against a battery whose voltage key is given as V. Again, I will assume this circuit to be m identical capacitors in series connected in n parallel branches. All right. So they are telling the individual capacitors cannot tolerate voltage more than 300. If there are m such capacitors, assuming that each of them has 300, 300, 300 along it, how many such capacitors can add up? Because potential difference across this arm of branch of capacitor is also battery voltage. So m times the number of capacitors times 300 plus 300 plus 300 so on, that should be nearly equal to the supplied voltage. Supplied voltage is 1000. So m should be 1000 by 300, and this shall give me around 3.3. 3.3 can't be the number, it's not a whole number. So I will have to assume 4. You may ask, why not 3? Because 3 is nearer than 4. Well, greater the number of capacitors in the branch, you know, better is the, uh, I mean, you can tolerate it more. If it is 3, imagine the number of capacitors is 3, not 4. Then what would happen to individual voltage across each capacitor? Then it would be 1000 by 3, which is definitely greater than 300. But 1000 by 4 is less than 300. So what is the minimum number of capacitors that can be connected in series? It is 4 in number. So far, so good. But the equivalent of all this should be equal to 2. That's the second condition. Two conditions. Individual voltages should be maximum 300, and the equivalent of this entire combination should be 2. How to maintain that? Now I know one thing, that there are just 4 capacitors in a series branch. I just need to figure out this n. How many such branches can be there? What is the equivalent capacitance of 4 capacitors in series? For 4 capacitors in series, 1, 1, 1, and 1. Well, it shall be 1 by 4. Each of them have 1, right? So it is 1 by 4. How many such branches can be there? Let there be n branches. What is the equivalent capacitance of those n times in parallel? So it is like 1 by 4, 1 by 4, 1 by 4, 1 by 4, so many. So how many such branches are there? N is what I told. And in capacitors, parallel arrangement, all the individual capacitances add up. So 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4 till n terms, it is n times 1 by 4. That should be equal to 2. So the number of branches should be equal to 8. So there are four capacitors in one line. And how many lines are there? There are 8 such lines. So 4 plus 4 plus 4 plus 4 plus 4, totally 8 lines. So how many capacitors are there? Totally there would be 32 capacitors. The minimum number, of capacitors required to achieve this would be 32. How come? 4 in one branch, 4 plus 4 plus 4 plus 4 plus 4, 8 such lines. 4 into 8 is 32. That is question number 24. Now, question number 25. Electric field is given as E equal to AX plus B. Constants are A and B equal to 20, B equal to 10. Potential at x1 is V1 and x equal to minus 5 is V2. And they're asking the potential difference. Okay, they're asking the potential difference. How to find potential difference? So what is the relation between electric field and potential? We know that relation for the 25th one is given as E equal to minus dV by dx. Electric field is given as 20 minus 10x, A plus bx, A minus bx or A plus bx, I'm unsure. It is Ax plus b. So 20x plus 10. It is given as 20x plus 10. Electric field is 20x plus 10. And that is equal to minus dV by dx. Now you can get the potential difference directly by integrating, which is 20x plus 10 dx integral. What is the final point? At x equal to 1, it is v1, x equal to minus 5, right? X equal to 1 and x equal to minus 5. Similarly, over here, it would be minus dv. At x equal to 1, what is the value? At x equal to 1, it is v1. And what is at x equal to minus 5? It is V2. From here itself, you can directly get V1 minus V2 and evaluate this expression, simple integration, 20x square by 2, or it is a 10x square plus 10x between the unknowns 1 and minus 5. You put the values over here, then you will find the V1 minus V2 term easily. That was question number 25. But before I close this video, I would want you to understand about these plates in some depth. What was the trick we used in this kind of a plate? So that is what I would like to, uh, elucidate further. How to deal with charging or charged plates. So the video is now titled Charged Conducting Plates. Okay. So here is where let's say it is Q1, let's say it's Q2, let me have another plate Q3. How to determine the charge distribution? Well, you see, what happens is once I place some charge, right, the the faces which are facing each other, the surfaces which are facing each other, will always have opposite charges. So if Q1 is there, let me assume Q developed over here. Then minus Q will develop on the left face of Q2. What is the charge on the right face of Q2? On the right face of Q2, the total overall charge given to this face is Q2. On one side, there is minus Q. What should be the other side? It will be Q2 plus Q, charge conservation. If it is Q2 plus Q on the right face, what should be the charge on the left face of Q3? You see, facing surfaces will always have equal and opposite charges. So if it is Q2 plus Q over here, for this side, it should be minus of Q2 plus Q. If it is minus Q2 plus Q for this, what should be the charge facing outside? Charge conservation, it should be Q3 minus of this, which should be Q3 plus Q2 plus Q. So how does the overall charge distribution look? It looks like this. And what should be the charge over there? It should be Q1 minus Q. Sum of the charges on a given plate, sum of the charges on a given plate is always the charge which is sum of the charges on two opposite surfaces on two surfaces of a given plate is always a charge given to the plate, charge conservation. You see, if I add Q1 minus Q and Q, I get Q1. Minus Q and Q2 plus Q, I'll get Q2. Minus of Q2 plus Q and Q3 plus Q2 plus Q, I'll get Q3. With this, I can determine the value of Q. How? By looking at one point inside this first sheet. Let me call that point as A. Right? Now see that the point A is located inside a conductor. So the field at A should be zero. That is how we have defined a conductor. There can't be electric field inside the conductor. Now we see this. What is the field due to this charge distribution at A? Remember that sigma by 2 epsilon naught thing. So it is Q by 2 epsilon naught. It is pointing inwards. Reason? Because this charge Q is positive, assuming. Now minus Q, from minus Q, what would be it? It would be the same field pointing outward. Why? Because the field due to a uniformly charged sheet, it doesn't depend on distance. So due to plus Q, if it is in this direction, due to minus Q, it will be equal, but in this direction. What about due to Q2 plus Q? Remember, Q2 plus Q is positive. Due to this also, the field here will be in this direction. But due to minus of Q2 plus Q, it will be in the opposite direction, pointing inward. All these arrows are equal but opposite in magnitude, they cancel. only two arrows remain. Arrow due to this and arrow due to that. And see, by default, both of them are positive in nature. So Q1 minus Q, right? The field due to this is pointing like this. The field due to that will point like that. Those two fields should be equal. So Q1 minus Q should be equal to Q3 plus Q2 plus Q. Therefore, I get the charge small q as Q1 minus Q2 plus Q3 whole by 2, right? So this is how we arrive at the charge distribution. Once I get to know small q in terms of the big Q1, Q2s, Q3s, I can easily determine what are the charges on the individual things. What is the funda? The funda is the field inside a conductor is always zero. That would be the discussion. You may see I have put only charge here. I didn't put any K term or epsilon naught term because they will cancel each other out. That's why I didn't put K or epsilon. Uh, so Q1 minus Q should be equal to Q3 plus Q2 plus Q. This is for three sheets, which is in JEE advanced. In the JEE main, you shall get only two such sheets, which would mean you will get one sheet having Q1, other sheet having Q2. Now, how will you find the charge distributions Q1 and Q2? I will assume one such on the right face of Q1 there is a small q charge. On the left face of Q2 there will be minus q charge. Charge conservation. If the total charge is Q1, this charge is Q, this one would be Q1 minus Q. If this charge is minus Q, this one would be Q2 plus Q. I will go by the same reasoning. I will consider a point A on this where total field has to be 0. Field due to this Q and this minus Q cancel each other out, leaving me with Q1 minus Q. Field due to this is pointing like this. Field due to this is pointing like that. Both should cancel. Q1 minus Q should be equal to Q2 plus Q. So the charge Q is Q1 minus Q2 by 2. So what is the charge developed on the inner faces? The charge developed on the inner faces is, if this is Q1 and this is Q2, Q1 minus Q2 by 2 and minus of Q1 minus Q2 by 2. What is the charge developed on the outer faces? It will be Q1 plus Q2 by 2 here, and here it would be, it is Q2 plus, this is Q1 minus Q, right? So on this face, it would be Q2 plus Q, which is Q2 plus Q1 minus Q2 by 2. Hence, here it should be Q1 minus Q2 by 2. On the outer surfaces, you have these charges. But remember, inner surfaces, you have Q1 minus Q2 by 2 and minus of Q1 minus Q2 by 2. This becomes the charge. This charge is exactly what we have to consider the inner one for the capacitor. Whatever Q comes here, it is this Q equal to CV. I need to consider any one charge. I will consider the positive charge on the inner plate. So in that question in our JE paper, this Q was 4 minus 2 by 2, or in other words, this was 1. Capacitance was given as 1. So the potential difference between the plates of the capacitor is also 1 volt. This is how you calculate charge distributions on conducting sheets, right? Because field inside a conductor is 0. So with this, we wrap up this discussion of JEE test paper 3. I hope you have had good number of insights over here. Like we have made approximations, we have developed techniques, especially voltage divider and charge distribution on a pair of given metallic sheets or conducting sheets. Thank you very much for your patience. Till next time, keep doing physics, have fun with physics, and take care. All the best.